Right now, at this exact moment, a galaxy is hurtling toward us at approximately 110 kilometers every single second. Not drifting. Not wandering. Hurtling. It is the largest structure within millions of light-years of our cosmic position. It contains 1 trillion stars. 1 trillion. And for over a century, astronomers believed it was smaller than our own Milky Way. They believed our galaxy was the dominant force in our local cosmic neighborhood. They were confident. They were wrong. Recent measurements have revealed something that has shaken the foundations of our understanding. Andromeda is not smaller. It is not comparable. It is vast on a scale that makes our previous estimates look almost embarrassingly inadequate. And what that discovery means for the collision that is absolutely inevitable, for the future of every star in both galaxies, for our entire cosmic destiny, fundamentally reshapes how we understand our place in this universe. The galaxy bearing down on us is far more enormous than anyone imagined. And we are directly in its path. If you want to understand why the true size of a distant galaxy changes everything we thought we knew about our cosmic future, hit that like button and subscribe right now. This discovery will permanently change how you see the night sky. Get comfortable. Let's begin. Before we can appreciate why Andromeda's true size matters so profoundly, we need to understand what Andromeda actually is and why it occupies such a unique position in human astronomy. Because Andromeda is not just another galaxy scattered across the observable universe. It holds a distinction that no other deep sky object can claim. Andromeda is the most distant object visible to the naked human eye. On a clear night, far from city lights, if you know exactly where to look in the constellation that bears its name, you can see it without any telescope, without any binoculars, without any optical assistance whatsoever. It appears as a faint fuzzy smudge of light, unremarkable at first glance, easy to dismiss as a cloud or an artifact of tired eyes. But that smudge is not a cloud. It is an entire galaxy. A vast rotating disk of 1 trillion stars, billions of planets, countless moons and asteroids and comets, all bound together by gravity into a structure so enormous that even light requires hundreds of thousands of years to cross it. The light from Andromeda that reaches your eyes tonight has been traveling for approximately 2.5 million years. Think about what that means. Those photons left Andromeda when our ancestors, Homo habilis, were just beginning to shape the first crude stone tools on the plains of East Africa. Those photons traveled through the absolute vacuum of intergalactic space for 2.5 million years while ice ages swept across Earth and retreated. While species evolved and went extinct. While continents drifted across the planetary surface through tectonic motion. While the entire drama of human evolution unfolded from primitive tool users to the species now reading these words. And all that time, those photons were traveling. Silently. Relentlessly. Crossing 2.5 million light-years of void at the maximum speed the universe allows. And tonight, right now, those ancient photons finally arrive at your retinas. They create an electrical signal that your brain interprets as a faint smudge of light. You are not seeing Andromeda as it is now. You are seeing Andromeda as it was 2.5 million years ago. You are looking backward through time. Every observation of Andromeda is an act of cosmic archaeology, recovering information from an era before humanity existed in its current form. Ancient observers noticed Andromeda long before they understood what it was. The Persian astronomer Abd al-Rahman al-Sufi described it in his book of fixed stars around 964 AD, calling it a small cloud. For nearly 1,000 years after that description, no one understood its true nature. It was catalogued, observed, sketched, and debated. Some astronomers believed it was a nebula within our own Milky Way, a cloud of gas illuminated by nearby stars. Others suspected it might be something more distant, more significant, more fundamental. The debate persisted because the technology to resolve the question simply did not exist. The breakthrough came in the 1920s through the work of Edwin Hubble. Using the 100-inch Hooker telescope at Mount Wilson Observatory, then the most powerful telescope on Earth, Hubble identified individual stars within the Andromeda Nebula. Specifically, he identified Cepheid variable stars, a type of star whose brightness fluctuates in a regular pattern directly related to its intrinsic luminosity. By comparing the apparent brightness of these Cepheids as seen from Earth with their known intrinsic brightness, Hubble could calculate their distance. The result was staggering. The Cepheids in Andromeda were far too distant to be part of the Milky Way. Andromeda was not a nebula within our galaxy. It was a separate galaxy entirely. An island universe. A vast collection of stars comparable to the Milky Way itself, located at an immense distance that placed it far beyond our galactic boundaries. This discovery transformed human understanding of the cosmos overnight. Before Hubble's measurement, many astronomers believed the Milky Way constituted the entire universe. Everything visible in the night sky was thought to be part of one single galactic system. Hubble demolished that assumption. The universe was not one galaxy. It was billions of galaxies. Perhaps trillions. Each one a vast collection of stars separated from its neighbors by millions of light-years of empty space. The cosmos expanded beyond comprehension in a single act of measurement. And Andromeda, that faint fuzzy smudge, became the first confirmed external galaxy, the proof that the universe extended far beyond our parochial boundaries. In the century since Hubble's discovery, Andromeda has been studied more intensely than any other galaxy besides our own. Astronomers have mapped its spiral structure, identified its central supermassive black hole, catalogued its globular clusters, analyzed its stellar populations, measured its rotation curve, and modeled its gravitational interactions with neighboring galaxies. The Milky Way and Andromeda together dominate what astronomers call the local group, a collection of approximately 80 galaxies bound together by mutual gravitational attraction. Most of the other members are small dwarf galaxies, gravitationally insignificant compared to the two giants. The Triangulum galaxy, the third largest member, contains only about 40 billion stars compared to the hundreds of billions or trillions in the Milky Way and Andromeda. The local group is fundamentally a two-body system. Two titans orbiting their common center of gravity, pulling smaller galaxies along in their gravitational wake. For decades, astronomers believed they understood the relative sizes of these two titans. They believed the Milky Way was slightly larger, slightly more massive, slightly more impressive. This belief shaped models of galactic dynamics, predictions about the inevitable collision, assessments of our cosmic significance. We were the bigger galaxy. We were dominant. Andromeda was our slightly smaller sibling. This assumption persisted for so long that it became embedded in textbooks, documentaries, popular science articles, and the general public understanding of our galactic neighborhood. But assumptions in science are only as good as the measurements supporting them. And the measurements were about to undergo a radical revision. Measuring the size of a galaxy sounds straightforward in principle. Point your telescope at the galaxy. Photograph it. Measure the angular extent. Calculate the physical size using the known distance. Simple. Except it is not simple at all. Not even close. The difficulty begins with a deceptively basic question that turns out to be almost philosophically complex. Where does a galaxy end? Consider what a galaxy actually looks like. The central regions are bright. Stars are densely packed. Light is abundant. Moving outward from the center, stellar density decreases gradually. The spiral arms become less prominent. The disk becomes thinner. Stars become sparser. The brightness fades. At some distance from the center, the galaxy's light becomes so faint that it blends into the background glow of the sky itself. There is no sharp edge. No boundary line. No wall marking where the galaxy stops and intergalactic space begins. The transition is gradual, continuous, and ultimately somewhat arbitrary. Where you choose to draw the boundary determines the size you measure. For decades, astronomers drew that boundary at the point where the surface brightness of the galaxy dropped below a certain threshold. This seemed reasonable. It was practical. It gave consistent results that could be compared across different galaxies. But it also systematically underestimated galactic sizes because it ignored the vast outer regions where stars still existed but were too faint and too sparse to exceed the brightness threshold. These outer regions, collectively called the stellar halo, surround the main disk like a vast diffuse cloud. The halo contains old stars, globular clusters, streams of stars torn from disrupted satellite galaxies, and enormous quantities of dark matter. It is real. It is gravitationally significant. And it extends far beyond the traditionally defined boundaries of the visible disk. The problem of measuring Andromeda's size was compounded by our viewing angle. We see Andromeda at an inclination of approximately 77 degrees from face-on. This means we are looking at the galaxy almost edge-on, which compresses its apparent dimensions and makes it harder to distinguish the full extent of the disk and halo structures. Additionally, Andromeda is so close that it spans a significant area on the sky, roughly 6 times the apparent diameter of the full moon when its faintest outer regions are included. Photographing such a large angular area with sufficient sensitivity to detect the outermost stars requires specialized wide-field instruments and extremely long exposure times. Early estimates of Andromeda's size focused on the bright central disk. This approach consistently yielded diameters in the range of 150,000 to 220,000 light-years. These numbers appeared in textbooks throughout the latter half of the 20th century. They were not wrong in the sense that they accurately described the bright visible disk. But they were incomplete. They told you the size of the city center while ignoring the vast suburbs that extended far beyond. The first serious hints that Andromeda was much larger than these estimates came from studies of its globular cluster system. Globular clusters are dense spherical collections of hundreds of thousands of old stars, gravitationally bound together and orbiting around a galaxy's center. The Milky Way possesses approximately 150 known globular clusters. Andromeda possesses over 500. And some of Andromeda's globular clusters orbit at enormous distances from the galactic center, far beyond the traditionally defined edge of the visible disk. If the galaxy's gravitational influence extended far enough to retain these clusters in stable orbits, then the galaxy itself must extend at least that far. The clusters were tracing out a galactic structure vastly larger than the visible disk alone. Then came the discovery of stellar streams. As Andromeda consumed smaller satellite galaxies through gravitational capture, the disrupted satellites left behind long filaments of stars stretching across enormous distances. These stellar streams, invisible to earlier telescopes but detectable with modern instruments, mapped out the gravitational field of Andromeda in stunning detail. The streams extended to distances of 200,000 light-years or more from Andromeda's center. They revealed that the galaxy's gravitational influence, and therefore its mass distribution, reached far beyond the visible disk. Andromeda was not merely a disk of stars 200,000 light-years across. It was a vast structure with gravitational reach extending to 300,000 light-years or more. The definitive evidence arrived through multiple converging research programs in the 2010s and 2020s. In 2015, a team led by researchers at the University of Notre Dame published results from a comprehensive study of Andromeda's stellar halo. Using data from the Pan-Andromeda Archaeological Survey, known as PANDAS, they mapped individual stars in Andromeda's outer halo with unprecedented depth and coverage. PANDAS used the Canada-France-Hawaii telescope to survey a region spanning approximately 400 square degrees of sky surrounding Andromeda. The survey detected millions of individual stars belonging to Andromeda's stellar halo, stars too faint and too sparse to appear in traditional galaxy photographs but nonetheless gravitationally bound to the galaxy and orbiting within its structure. The results were extraordinary. Andromeda's stellar halo extended to at least 230,000 light-years from the galactic center. In some directions, detectable stars continued even further. The halo was not uniform. It contained substructure, streams, shells, and overdensities created by the gravitational disruption of satellite galaxies over billions of years. But the overall extent was clear. Andromeda's gravitational domain, the volume of space within which stars were bound to the galaxy, was vastly larger than the visible disk alone. The galaxy's total diameter, including the stellar halo, exceeded 460,000 light-years. Possibly more. In 2020, a study using absorption measurements from background quasars provided even more dramatic results. Quasars are extraordinarily luminous objects powered by supermassive black holes in distant galaxies. Their light passes through intervening material on its way to Earth, and that material leaves absorption signatures in the quasar spectrum. By analyzing these absorption signatures, astronomers can detect gas associated with foreground galaxies even when that gas is too diffuse to emit detectable light of its own. This technique revealed that Andromeda's gaseous halo, the circumgalactic medium surrounding the visible galaxy, extended to approximately 1.3 million light-years from the galactic center. Not 100,000 light-years. Not 200,000. 1.3 million. This gaseous halo is not the stellar halo. It is even more extended. It represents the gas that is gravitationally bound to Andromeda, falling inward or being expelled outward through galactic processes, but remaining within the galaxy's sphere of gravitational influence. If Andromeda's gaseous halo extends to 1.3 million light-years, and the distance between the Milky Way and Andromeda is approximately 2.5 million light-years, then a simple calculation reveals something remarkable. Andromeda's gaseous halo extends more than halfway to the Milky Way. Our own galaxy likely possesses a similarly extended gaseous halo. This means the two galaxies are not separated by empty intergalactic space. Their gaseous halos may already overlap. The collision between the Milky Way and Andromeda may have already begun in the most tenuous sense. The outer atmospheres of the two galaxies may already be interacting, their gas clouds interpenetrating across the void. By the most comprehensive contemporary measurements, Andromeda's visible stellar disk extends approximately 220,000 to 260,000 light-years in diameter. Its stellar halo extends the total diameter to approximately 460,000 to 520,000 light-years. Its gaseous halo extends further still to a diameter exceeding 2.6 million light-years. The number you choose depends on what you mean by the galaxy. If you mean the bright visible disk, 220,000 to 260,000 light-years. If you include the stellar halo, roughly 500,000 light-years. If you include all gravitationally bound material including gas, over 2 million light-years. By any measure, Andromeda is enormous. By any definition, it is substantially larger than what textbooks described for decades. Now let us attempt to comprehend these dimensions in terms that might translate into human understanding. Consider the stellar disk alone at approximately 260,000 light-years in diameter. Light requires 260,000 years to cross Andromeda's disk. A message sent at the speed of light from one edge of Andromeda to the opposite edge would arrive after 260,000 years. The sender would be ancient history by the time the message arrived. The civilization that created it might have risen and fallen dozens of times. The language would be unrecognizable. The purpose might be forgotten. To construct a physical analogy, imagine reducing the entire Earth to the size of a marble, roughly 1 centimeter in diameter. At this scale, the Moon would be a tiny speck about 30 centimeters away. The Sun would be a grapefruit located approximately 120 meters distant. The nearest star would be another grapefruit located approximately 32,000 kilometers away, roughly the circumference of Earth. The Milky Way at this scale would be a disk approximately 100 million kilometers in diameter. And Andromeda would be a larger disk approximately 200 million kilometers in diameter, separated from the Milky Way by approximately 800 million kilometers. Even at this dramatically compressed scale, where Earth becomes a marble, the distances remain incomprehensibly large. Consider another approach. If you could travel at the speed of light, the absolute maximum velocity permitted by the laws of physics, and you departed from one edge of Andromeda heading for the opposite edge, your journey would consume 260,000 years. During that time, if you could somehow look back at Earth, you would watch roughly 13,000 generations of human civilization pass. Agriculture would be invented. Cities would rise. Empires would form and crumble. Every event in recorded human history would unfold and be forgotten and unfold again multiple times over. And you would still be traveling across a single galaxy. Not the universe. Not even the local group. A single galaxy. The star count compounds the enormity. Andromeda contains approximately 1 trillion stars. Current estimates range from 800 billion to 1.5 trillion depending on the methodology and assumptions used. 1 trillion represents a reasonable middle estimate. To appreciate what 1 trillion means, if you stacked 1 trillion $1 bills on top of each other, the stack would extend approximately 109,000 kilometers. That is more than 1/4 of the distance from Earth to the Moon. 1 trillion seconds equals approximately 31,700 years. 1 trillion stars in a single galaxy. Each star is a nuclear furnace converting hydrogen into helium through thermonuclear fusion. Each star radiates energy across the electromagnetic spectrum. Each star possesses its own gravitational influence, its own history spanning billions of years, its own orbital path around the galactic center. And around most of those stars orbit planets. If the pattern observed in our own galaxy holds for Andromeda, and there is no reason to believe otherwise, then most of Andromeda's trillion stars host at least one planetary companion. Many host multiple worlds. A conservative estimate suggests Andromeda contains at least 1 trillion planets. Some of those planets are rocky. Some are gas giants. Some orbit within the habitable zones of their stars where liquid water could theoretically exist on the surface. If even 1% of Andromeda's planets reside in habitable zones, that represents 10 billion potentially habitable worlds within a single galaxy. 10 billion worlds where conditions might permit the chemistry of life. 10 billion chances for biology to emerge. 10 billion potential homes for consciousness. Yet Andromeda's sheer size creates a paradox that is both humbling and haunting. The galaxy is so vast that meaningful communication across it appears functionally impossible. A signal traveling at light speed from one edge of Andromeda to the opposite edge requires 260,000 years. A round-trip exchange of information requires 520,000 years. No civilization, no matter how advanced, can maintain coherence across timescales that vast. Languages evolve beyond recognition within millennia. Cultures transform within centuries. Technologies become obsolete within decades. A message sent today from one edge of Andromeda might arrive at the far edge after 260,000 years to find that the intended recipient no longer exists, never existed, or has evolved into something utterly unrecognizable. The galaxy is large enough to contain trillions of worlds yet structured in a way that isolates them from each other through the tyranny of distance and the speed of light. Even within a single galaxy, the universe enforces cosmic loneliness. The mass of Andromeda reinforces the scale problem. Total mass estimates for the Andromeda galaxy have fluctuated significantly over the decades as measurement techniques improved. Early estimates suggested Andromeda was 2 to 3 times more massive than the Milky Way. This seemed consistent with its larger apparent size and higher star count. But more recent studies using refined measurements of stellar motions and satellite galaxy orbits have revised these estimates. Some studies suggest Andromeda's mass might be comparable to the Milky Way's. Others maintain that Andromeda is significantly more massive. The current best estimates place Andromeda's total mass, including dark matter, at approximately 1.5 trillion solar masses, compared to the Milky Way's approximately 1 to 1.5 trillion solar masses. The uncertainties remain large enough that definitive ranking is difficult. But the preponderance of evidence suggests Andromeda is at least as massive as the Milky Way and probably somewhat more so. This mass is dominated by dark matter. Visible matter, the stars and gas and dust that we can observe directly, constitutes only approximately 15 to 20% of Andromeda's total mass. The remaining 80 to 85% is dark matter, the invisible substance that does not emit, absorb, or reflect electromagnetic radiation but exerts gravitational influence on everything around it. Dark matter forms a vast spherical halo surrounding and permeating the visible galaxy. Without dark matter, Andromeda would not exist in its current form. The outer stars would fly away into intergalactic space. The disk would dissolve. The spiral structure would collapse. Dark matter provides the gravitational scaffolding that holds the entire visible galaxy together. It is the skeleton upon which the flesh of stars and gas is hung. The discovery that Andromeda is vastly larger than previously believed has profound implications for the collision that will occur between our two galaxies. This collision is not speculative. It is not theoretical. It is an observed fact of gravitational physics. Andromeda and the Milky Way are approaching each other at approximately 110 km per second. At this velocity, the remaining distance of 2.5 million light-years will be closed in approximately 4.5 billion years. The merger is inevitable. The two galaxies are locked together by mutual gravitational attraction that neither can escape. Every second, the distance between us decreases by 110 kilometers. Every minute, by 6,600 kilometers. Every year, by approximately 3.5 billion kilometers. The countdown is in progress and has been in progress since both galaxies formed billions of years ago. Previous simulations of this collision assumed the two galaxies were similar in size and mass. The merger was modeled as a collision between approximate equals, resulting in a moderately chaotic interaction that would gradually reshape both galaxies into a single elliptical galaxy over billions of years. But if Andromeda is substantially larger than previously believed, the dynamics change significantly. A more massive Andromeda means a more asymmetric collision. The Milky Way will be the smaller partner. Our galaxy will be more severely disrupted. Our spiral arms will be torn apart more completely. Our stellar populations will be scattered more dramatically. The merged galaxy will resemble Andromeda more than the Milky Way. We will not merge with an equal. We will be absorbed by a giant. Computer simulations of the collision, updated with the revised size and mass estimates, show a dramatic sequence of events. In approximately 4 billion years, Andromeda will begin to dominate the night sky. It will appear as a disk of light that grows larger and brighter over hundreds of millions of years. Eventually it will span a significant portion of the sky, far larger than any celestial object visible from Earth today. Then the two galaxies will make their first close passage. The gravitational interaction will distort both galaxies, pulling out long tidal tails of stars and gas. Some stars will be flung into intergalactic space, never to return. The spiral structure of both galaxies will be severely disrupted. Star formation rates will spike dramatically as gas clouds compressed by gravitational forces collapse to form new stars in an intense burst of stellar activity. After the first passage, the two galaxies will separate briefly before gravitational attraction pulls them back together for a second, closer encounter. Each successive passage will be closer and more violent than the last. Stars will change orbits. Planetary systems will be perturbed. The ordered structure of spiral arms will dissolve into chaos. Eventually, after multiple passages spanning billions of years, the two galaxies will fully merge. The resulting structure will be a massive elliptical galaxy, sometimes speculatively named Milkomeda or Milkdromeda by astronomers who enjoy portmanteau names. This merged galaxy will contain the combined stellar populations of both parent galaxies, roughly 2 trillion stars, orbiting a central supermassive black hole formed by the merger of the Milky Way's and Andromeda's respective central black holes. Our solar system will almost certainly survive the merger physically intact. Despite the dramatic imagery of galactic collision, the distances between individual stars are so enormous that direct stellar collisions during the merger will be extraordinarily rare. Stars will pass each other like ships in an ocean, separated by light-years of empty space even during the most chaotic phases of the interaction. Our Sun will be displaced from its current orbit, moved to a new position within the merged galaxy. But our planetary system will likely remain bound together. Earth will continue orbiting the Sun. The Moon will continue orbiting Earth. The immediate physical danger to our solar system from the merger itself is minimal. However, by the time the merger occurs, approximately 4.5 billion years from now, our solar system will be facing its own internal crisis. The Sun will have nearly exhausted its hydrogen fuel. Solar luminosity will have increased substantially, raising Earth's surface temperature above the point where liquid water can exist. The oceans will have evaporated. The atmosphere will have been transformed. Earth will be approaching the end of its habitable lifetime regardless of what happens on the galactic scale. The merger with Andromeda is cosmically significant but personally irrelevant to the fate of life on Earth. Our planet's destiny is determined by stellar physics, not galactic dynamics. This brings us to the deeper philosophical significance of Andromeda's true size. The discovery that our nearest large galactic neighbor is vastly larger than we believed continues a pattern that has defined human astronomy for centuries. A pattern of cosmic demotion. Of discovering that we are less central, less significant, less special than we assumed. Copernicus moved Earth from the center of the solar system. Herschel moved our solar system from the center of the galaxy. Hubble moved our galaxy from the center of the universe. And now, the revised measurements of Andromeda move our galaxy from a position of relative dominance in the local group to a position of relative subordination. We are not the biggest galaxy in our neighborhood. We are the second biggest. Andromeda is larger. Andromeda is probably more massive. Andromeda will dominate the merger when it comes. Each of these demotions has been accompanied by a corresponding expansion of our understanding. Yes, we are less central. But we understand more. Yes, we are less significant. But our knowledge is more profound. The act of discovering our own cosmic insignificance is itself a remarkable demonstration of significance. No other known species has done this. No other known intelligence has measured the dimensions of distant galaxies, calculated the timelines of cosmic collisions, or contemplated its own position within the vast architecture of the universe. We are small. But we understand that we are small. And understanding is not nothing. Understanding is arguably the most remarkable thing the universe has produced. Andromeda contains 1 trillion stars. Around those stars orbit trillions of planets. On some of those planets, conditions may permit liquid water, complex chemistry, and perhaps life. Somewhere in that vast galactic structure, on a world we will never see through any telescope, consciousness may have already emerged. Beings may be looking up at their own night sky, seeing our Milky Way as a faint fuzzy smudge, wondering about the galaxy that is hurtling toward them. They may have their own astronomers, their own telescopes, their own measurements of galactic size. They may have discovered that the galaxy approaching them is smaller than they previously believed. They may be contemplating the collision, the merger, the transformation of their cosmic neighborhood. Or they may not exist at all. Andromeda's trillion stars may orbit in magnificent solitude, their planets barren, their worlds lifeless, their beauty witnessed by no one. We cannot know. The distance is too great. The timescales are too vast. The light we observe from Andromeda is 2.5 million years old. Whatever is happening there now will not become known to us for another 2.5 million years. We are separated from our nearest large galactic neighbor by a gulf of time as well as space. The universe enforces this isolation not through malice but through geometry. The speed of light is the universe's speed limit. Distance is real. Time is real. And both conspire to keep us separated from any civilization that might exist within Andromeda's trillion-star embrace. Yet the knowledge itself has value. Knowing that Andromeda is larger than we thought, knowing that it contains more stars, more planets, more potential worlds, knowing that it will eventually collide with and absorb our galaxy, this knowledge changes our perspective in ways that transcend mere facts. It places us within a cosmic context that is simultaneously humbling and elevating. We are small, but we understand enormity. We are brief, but we contemplate eternity. We are confined to a single world, but we have measured the dimensions of galaxies millions of light-years distant. This is not nothing. This is extraordinary. The Milky Way and Andromeda are falling toward each other. The distance closes by 110 kilometers every second. Every moment of your life, every breath you take, every heartbeat, brings the two galaxies fractionally closer. The collision is written into the fabric of gravitational physics as surely as the sunrise is written into the rotation of Earth. It will happen. Nothing can prevent it. And when it does, billions of years from now, The universe will contain one galaxy where there were once two. The combined structure will be vast, containing roughly 2 trillion stars and untold trillions of planets. It will be a monument to gravitational inevitability, a merged structure born from the collision of two cosmic titans, one of which we called home. Andromeda hangs in the night sky tonight. That faint fuzzy smudge visible to the naked eye from dark locations. It looks peaceful. It looks distant. It looks harmless. It is none of these things. It is 1 trillion stars bearing down on us at 110 kilometers per second. It is a galaxy far larger than we believed for a century, far more massive, far more dominant in our local cosmic neighborhood. It will consume us. It will absorb our galaxy into its own structure. It will transform our cosmic home beyond recognition. And it will do all of this with the quiet, unstoppable patience of gravity acting across the void. Look up tonight if you can. Find that fuzzy smudge. Know what it is. Know how large it truly is. Know what it means for the future of every star in our galaxy. Know that the photons reaching your eyes have been traveling for 2.5 million years. And know that in another 4.5 billion years, there will be no separation between us and Andromeda. The two galaxies will be one. The night sky will look nothing like it does today. And whatever conscious beings exist at that time, on whatever world they inhabit, will see a galaxy shaped by the collision of titans, a galaxy born from the merger of two vast structures, one of which we once called home and the other we once called Andromeda. They will not see the separation that we see tonight. They will see only the result. Only the merger. Only the combined structure. The history of two separate galaxies will have dissolved into a single gravitational embrace from which neither can escape. That is what it means to finally know how big Andromeda is. It is not merely a number. It is not merely a measurement. It is a revelation about the future of everything we know. The galaxy approaching us is enormous. The collision is inevitable. The merger will be transformative. And we are the generation that finally understood the scale of what is coming. So here is my question for you in the comments. Knowing that Andromeda is far larger than we thought and that the collision is inevitable, does this change how you feel about our place in the cosmos? Does it humble you, frighten you, or inspire you? And consider this, if civilizations exist within Andromeda right now, looking at our Milky Way, do you think they have measured our size too? Do you think they know we are coming? Or are they, like us, only beginning to understand the true scale of the galaxy bearing down on them? Let me know your thoughts below. I am genuinely curious about your perspective on this. Let us discuss it together.